Hi everyone, my name is Christine Pacewicz and I am an assistant professor at Saginaw Valley State University. Thank you for attending my virtual presentation focused on applying latent growth curve modeling in the field of exercise science. Within the field of exercise science, common aims are to describe, understand, and explain change, both within and between individuals. To accomplish these aims focused on change, we need to collect multiple measurements across time. Such designs afford the assessment of change and development. For instance, longitudinal work can help us examine trajectories of physical activity from childhood to adolescence, from adolescence to adulthood. We can also use such designs to assess if attitudes about physical activity and competence perceptions change across an intervention. Latent growth curve modeling is one analytical approach that is useful for such work. Because of the recent call for studies with multiple measurement points, the increasing use of LGCM in the field, and the ability to extend latent growth curve modeling to fit an array of research questions, the purpose of the current study was to describe and demonstrate the use of latent growth curve modeling within the field of exercise science to help facilitate the effective use of this technique and encourage the use of longitudinal study designs. Latent growth curve modeling is an analytical technique that fits growth curve models in the structural equation modeling framework, enabling the assessment of when change happens, inter-individual differences in when change happens, and why change may happen. This approach enables the assessment of both observed and latent variables. We also can assess residual or measurement error. These characteristics distinguish latent growth curve modeling from traditional methods of change. Before using latent growth curve modeling, a model must be predicted. We can examine different theories of change, including a no change model, a linear model or constant rate of change model, and a latent basis model or a non-constant change model where change is not predetermined. In practice, multiple models can be fit based on developmental theory to find the best fitting change model prior to assessing predictors of change. We call this the unconditional latent change model. Fit is examined using various fit indices, including but not limited to the chi-square test, the comparative fit index, the root mean square error of approximation, also known as RMSEA, and the RMSEA close fit test. The data used in this illustration come from the Michigan State Longitudinal Motor Performance Study. Participants included 267 girls with possible measurement occasions from age 8 to 16 years. So in total, there were 17 possible measurement occasions. We first examined unconditional latent change models for two motor performance tasks, the jump and reach and the 30-yard dash. In these models, we included structured residuals. In other words, residuals of observed repeated measures are directly regressed on one another. This extension is appropriate when theory suggests that the measurements are related over time. In other words, if a prior measurement is suggested to causally influence a future measurement. Examination of fit indices suggested that the latent basis model fit the data best for both the jump and reach and the 30-yard dash. Thus, these models were used to assess predictors of growth. Specifically, we assessed if maturational status, a time invariant predictor, predicted the intercept or the baseline and the slope or the change of the two motor tasks. Two dummy variables were created to assess differences between early, average, and late maturers. What is important to recognize here is that predictors can be time variant, which means that they change over time, or time invariant, which means they do not change over time, such as maturational status. Predictors are added to the model after we find the best fitting change model. This is why we call this model the conditional latent change model. Using latent growth curve modeling has a variety of strengths, including the ability to test multiple theories of change, using extensions including structural residuals, and the ability to assess determinants of change. However, when using LGCM, the hypothesized and model pattern of change is the same for all participants. Thus, if there is heterogeneity within the change process among participants, this will not be captured using latent growth curve modeling. As a result, this can influence parameter estimates and overall conclusions drawn. Additionally, the spacing between measurements can influence the observed change pattern, and there is a need for a large number of observations at each measurement occasion. Future work within the field could use structural residuals to more fully understand change when measurement occasions are theoretically linked. For example, when modeling changes in physical activity levels across an intervention, this extension of latent growth curve modeling may be useful as prior physical activity levels may influence future physical activity levels. Thank you for listening to my presentation. If you want greater detail on the measurement and structural model equations that could not be presented today, I can be reached by the email address presented on the screen. Thank you.